So, welcome to the third lecture of circular dichroism. So, students, we talked how we can make the light polarized linearly as well as circularly. We saw the application of linearly polarized light to determining the concentration of sugar. It can be in food, it can beverage, it can be in like a just honey purity, also clinical application by measuring the blood glucose level. One can use this linearly polarized light. In details, we also talked to you about the application of circularly polarized light, and that is a beautiful technique that is used for protein secondary structure or even tertiary structure determination. We talked a little bit about instrumentation and concept. So, a chiral molecule, which plenty of them are in protein, all the amino acid except one are chiral, right. So, chiral molecule absorbs differentially this right handed and left handed polarized light, right, and that we measure as a theta, that is a ellipticity. We can convert this ellipticity value by some mathematical operation, by essentially factoring the concentration into molar ellipticity, and one can use for your secondary structure calculation. By there are some software, we talked about the Bestel and all those, they fit it. We also talked, if we want to just compare two protein, their CD signal and all those, you just factor into the number of residue, that is called mean residue ellipticity, and you can use for comparing the two protein CD signal. We also looked at the application of this in a therapeutic protein, the quality control and all those, right. So, concept remains same, your protein is going to absorb differentially the right handed and left handed polarized light, and it is giving a signal which is measured in terms of ellipticity, right. So, let us move forward and we can just go to the again concept. So, we are measuring this 3D signal into two region. One is far UV region 165 to 250 nanometer, another is near UV region 250 to 320. What is the chromophore in this far UV region? It is a peptide bond minus CONH. Essentially, we are measuring this CONH, and that is what you remember changes when we look at the secondary structure, right. So, this is what we measure. In the near UV, we are measuring the aromatic amino acid, the 3 aromatic amino acid, tyrosine, tryptophan, phenylalanine. The transition that is happening for peptide bond, coming back to your UV visible concept, it is a N non bonded to anti bonding pi N to pi star, here it is pi to pi star. In near UV, we are going to have pi to pi star and N to pi star, this kind of like a homo-lumo, you remember the concept. So, this kind of transition we are having. The absorbing species here is CO in the backbone. Essentially, these are the 3 tryptophan, tyrosine and phenylalanine at different wavelength they absorb. Far UV is used for secondary structure determination, near UV is used for tertiary structure determination, also probing the environment of these probes, tryptophan, tyrosine, phenylalanine. Typical band that we get in a CDS spectra at 222 to 8 for a helix, 215 for like a beta sheet, and positive band 193. Here we get it around the 272, 282 and 262 in the near UV region. Sensitivity far UV is very high. So, if you look at epsilon, it is a 5000 to 10,000. Here it is a medium, not so high. So, you require more concentration for near UV than far UV, and therefore, sample requirement here is 0.1 to 0.5 mg per ml, here 0.5 to 2 mg per ml. The path length that we have is a narrow path length you require for far UV 0.1 mm, here you require 1 mm to 1 cm, and spectral resolution is sharp narrow band, it is a overlapping and complex band that we get, right. So, far UV CD peptide bond we are measuring, right. So, peptide bond it is a CONH. The transition that we talked about happening N to pi star or pi to pi star. That shows a strong CD signal due to regular dihedral angle. So, if you remember the phi and psi, right, from your these are the dihedral angles. So, here is a beta sheet, alpha helix, all those you remember coming from the secondary structure. So, you have the dihedral angle, and that is basically done in CONH bond. So, for alpha helix, if you remember, where are the phi and psi? This is my Ramachandran plot, phi and psi. Here is alpha helix, right. So, here is 0 plus 180 minus 180, 0 plus 180. So, this is alpha helix. This alpha helix, say phi is minus 60, psi is minus 45. We have two negative band, minus 222 and 208. Now, this is the molar absorptivity of the 222, this is for 208, and that is what we get a double minima structure for an helix here and here. That is what double minima structure you have. Then in the beta sheet falls in the Ramachandran plot in this region, right. So, in this region you have that gives you single negative peak around 280. You get here the theta at 280 about 1600 degree per centimeter square per decimole, and it is a broader than a helix. Then random coil, it is a irregular dihedral angle. You do not know whether the dihedral angle is coming in this region, which region it is coming, and therefore, it is a weak and flat signal, because its molar absorptivity or theta is very like a low, also 2000 degree centimeter per decimal. So, baseline like appearance it has. So, if this is a helix, your random coil will come somewhere here, right. And now, because they have a characteristic peak for helix sheet random coil, you can have a measured spectrum and you fit in some equation 0.45 into alpha helix, 0.35 into beta sheet, 0.2 is into random coil, and that basically can give you the secondary structure determination. For the tertiary structure, you can have the aromatic amino acid that sends the tertiary structure, and that happens by a chirality or asymmetric core. The electric field near that changes, and that gives you idea in the far UV, near UV CD. So, aromatic signal tryptophan 280, because you have a indole ring, it is the most sensitive to the environment. Tyrosine at 274, it has a phenolic OH, it participates in hydrogen bonding and then shift can happen. And phenylalanine, it is a weak one, benzene ring we have, and buried residue. So, looking at all these three aromatic acid, we get the environment of a protein, which is typically measured in the tertiary structure determination. So, here you have the far UV CD signal of a helix. You look at here, one band here, one band here, peptide bond of CO N to pi star, pi to pi star. Here you have a secondary structure comparison that I was saying. In CD, alpha helix is more sensitive than the beta sheet and random coil. So, alpha helix 2 down CD signal 222, 208. In beta sheet, it is a 218 and random coil very little signal, some around 205 or so, but it is mostly flat. So, these are typical signature for alpha helix, random coil and beta sheet, and this is basically we use for deconvolution, right. Now, in near UV CD signal, we have a total CD signal, something comes like this in this region. You have a phenylalanine, tyrosine, tryptophan. So, all are contributing here, right. This is giving some signal in this region. So, aromatic residue senses the compactness of a protein, that we call it tertiary structure, and this structure happens by a chirality or a symmetric protein core. There is electric field that changes nearby, and you have a hydrogen bonding pattern that can also changes. So, we deconvolute signal, or we have a contribution from signal 280 from tryptophan, 274 from tyrosine and 254 for phenylalanine. So, but resultant signal comes like this, and this can also change whether it is hydrogen bonded, it is buried inside or whatever. So, that contribution gives you idea about tertiary structure, right. So, near UV CD aromatic residue environment it is sensing. So, in case of say if you have a secondary structure, you get a very beautiful CD signal 2D here and here, but if you unfold it, it becomes very minimal signal, just about line. So, you can monitor this change as the protein folds, from these two very nicely deep structure of 208 to 22 in a helical protein, it goes to more like a random coil. So, application where we have a application in protein folding or unfolding, aromatic signal collapse upon denaturation. So, that is what we see here. Now, beautifully, if suppose this is my unfolded protein and it binds to a ligand, it can adopt the structure, right. So, you can adopt the structure that will taking the structure upon binding. So, here you have a folded structure. Now, ligand binding tryptophan interacts and you can have a substrate inhibitor interaction, protein interaction, two protein interactions, some structural changes that we can monitor it, because whatever structural change that is happening and noticeable, one can measure it. So, for a fully folded protein, you have a theta at 280 degree, you can have 3000 degree per. If a partially folded, you see a reduced amplitude, and fully denatured you have near 0. So, looking at this, you can find it out how the protein is folding. So, essentially the far UVCD and near UVCD, you can get the protein, complete protein structure, secondary structure as well as tertiary structure. So, combine both of these techniques, secondary and tertiary, you can get a complete assessment of the protein structure. Now, some of the data analytics and deconvolution method that we talked about. Data quality is very important, because to deconvolute you have to have a good signal to noise ratio. So, signal to noise can come from whatever CD signal we are getting. So, here you see this is good signal to noise, here it is coming along bad baseline. So, it is not so good signal to noise. So, excellent signal to noise should be having 100 signal 1 noise, good can be 50 to 100, acceptable even can be 10 to 50, but poor will be less than 10, right. So, target in all those CD measurement, we should have at least 50 to 1 signal to noise for reliable deconvolution. How do you do that? Either by increasing the path length or by increasing the protein concentration. If your concentration is not good, your CD signal will not give you enough signal. So, one has to tune with a signal and get a good CD signal. Sometimes rather than choosing the very thin qubit, you can little bit increase it, so that it absorbs more. So, that is how you do, your target should be more than 50 for a reliable deconvolution, and you have to also get the root mean square deviation, like your fitting and actual signals should have a very less deviation, like excellent will be RMSE less than 0.01 for a excellent fit, then good fit will be 0.01 to 0.005, acceptable it will be 0.005 to 0.1. Some spectral anomaly can also come. So, in the normal alpha helix, basically you have a double minima, but if there is aggregates or interference is happening because of that, then it will deviate, and you can measure that by measuring theta at 250 nanometer and theta at 225 divided by theta at 222. If it is normal, then it will be less than like our 0 or 0.005, it is more than 0.1, then aggregates or interference is happening, right. So, that is a data quality matrix that one can measure it. Now, deconvolution algorithm, Bestel or dichrome that we talked about, basically it is normalize the spectrum by taking the lambda at any wavelength, lambda minima, lambda maxima, and then you require a basis set, right, 4 state helix, sheet, turn, random coil, 8 state one can have also the mixture of this, add alpha beta turn, anti-parallel and all those. So, this automatically neural network based software they are there and fetch the information from database. To do a linear square fit, you fit it basically your actual data minus the whatever coming from predicted data, and you have to have some fractional bounding and completeness of this fitting. So, do in a iterative loop and then get it there. The final step is bootstrap error analysis. You find how much minimum error you have, and you can calculate with a 90% confidence with a less interval, then you can say that prediction is coming good, right. So, it is also an art that one has to learn. So, how interpret this result? So, you can take it any of these software Bestel, K2D and all those. Basically, this has a database, it is a ML trained and you can have a very good resolution. This CDNN takes 4 state beta, alpha, turn, coil. K2 3 take only 3 state alpha, beta, coil. Bestel takes 8 state, it is a auto select those states, and then Contine takes 8 to 20 stable states, that is a variable. So, for folded protein, an example if you take it, alpha helix about 60%, beta sheet 23% turn and coil, and root mean square error is less, signal to noise is good. So, you can conclude that it is a well folded protein with secondary structure. Take an example of partially folded protein, partially unfolded. Alpha helix is 35%, beta sheet is 15%, coil is this, turn is 8%, coil is very high 42%. Error is 0.015% and signal to noise is not so good 45 to 1. So, you have loss of a secondary structure or lots of coils are there. It suggests that protein is either denatured or aggregated or disordered, something like this it is there. You can have an anomalous or aggregation signal that may come. So, you have a RMS high, signal to noise very poor, and then spectral anomaly that I talked about this. You do this calculation theta to 15 minus theta to 25. So, it tells you about the likely aggregates or scattering is happening. For scattering you can reduce the or aggregation you can reduce the concentration, sonicate it, filter it and remove all these aggregates, and then probably you can get a better data, right. So, let us look at some of the application in protein folding and unfolding studies, right. So, suppose protein is in the folded state, which is a compact state here, and then it is going to unfolded state, something like this. So, these experiments we can do by measuring the CD signal at say 222 where helix is there and increasing the temperature. So, we put the cuvette and then we have a instrument that is called Peltier that increases the temperature. We are increasing 20, 30, 40, 50 and measuring the 222 CD signal. So, this says the folded state and this will say unfolded state, and this is the folding transition midpoint is 65 degree. So, for you can calculate the fraction of unfolding by measuring the folded state signal at any temperature signal and unfolded state signal. That is what one can do, two state folding and unfolding, fractional unfolding with temperature. You can also use for clinical relevance, you can predict the protein therapeutic shelf life, because when we make a protein, we do not make it to be used immediately, you can store medicine for a long time. So, you can look at during the shelf life of this protein how much folded unfolded comes, right. So, one can have a protein therapeutics predicting the shelf life, storage condition at 4 degree, how long it can stay or something like that. You can find a disease mutation happens in protein and that changes the misfolding or induce the misfolding, protein stability changes. So, one can find it out what disease mutation is doing, and then you can have a chaperone screening, because chaperone makes sometimes stable protein. So, one can find which protein is stabilizing your protein. So, all those application you can have it. You can have a like a DNA or RNA conformation, you can find the B type, A type, Z type or I motif, quadruplex motif, looking at their CD signal at different wavelength, which is given here. So, at 265 this is positive, A form at 250 minus 210, it is a biphasic. So, essentially you can find it out a structure of whether it is Watson Crick double helix or it is tilted helix or it is a GC reach or AT reach, what kind of conformation of DNA you have. So, here you look at this conformation is a B type, this is 2 at A type, this one is Z type, so left handed. So, nucleic acid structural conformation you can have. One can find it out for drug screening like an intercalation ethidium bromide which can binds to the B DNA, you can find it out which is actually which kind of molecule is interacting and changing the structure. You can find it RNA structure like if it is having hairpin, bulge, pseudoknots, what kind of. You can have a modification in the nucleic acid like epigenetic application. If 5-methylcytosine it is a modified base, changes the spectrum. You can have in gene therapy, monitor the antisense nucleotide folding that is coming because of this, right. So, all these application of a nucleic acid you can have. Similarly, you can have the structure of quadruplex like a G quadruplex and all those. So, quadruplex forms upon binding to the metal ion. You can have parallel anti-parallel hybrid topology. You can have a lambda 263 to 95 and you can have this, if it is strong positive signal of parallel, you know that it is a strong telomere or cancer related. So, even you can analyze the DNA that is coming to find it out what kind of complication one can have in the DNA. So, if it is anti-parallel, you have a weak and positive bimodal, it is a regulatory sequence. If it is hybrid, you can have a telomere mixed conformer. So, looking at the pattern and the changes in that pattern, you can find it out the quadruplex stability, architecture and what could be their function in the body, right. So, yeah. So, clinical application you can use this as a cancer biomarker like a telomerase increases in the cancer. So, telomerase is active in 85% of cancer. So, you can measure it how it is increasing, maintain the telomerase with age, then one can have a quadruplex formation in the blood. So, you can measure the CD signal and see the change that is happening. So, thermal stability and protein therapeutics, already I talked about monoclonal antibody, fusion protein, engineered enzyme, one can measure the stability of that. Like here you can look at this MAB is good because it is denaturing at a higher temperature, then this MAB is denaturing fast, this has failed. You just by CD you saw that this is not good for therapeutic application. So, MAB therapeutics quality control one can find it out, batch to batch variation you can find it out, storage and shelf life you can find it out. So, here you see we have a clinical application looking at the DNA conformation and here you have a therapeutic application looking at the MAB stability and storage condition and all those. Right. So, this is the summary comparative spectroscopic technique that we talked about CD, FTIR, Raman, UV visible, NMR and X-ray I have not talked to, but these are again for sake of summary we have put it. So, what is the physical basis, the wavelength, sample amount, all of these we have discussed. You can just take your time to go through it and compare with the two advanced technique that is NMR and crystallography, how this I would say low resolution, but quicker techniques help you in getting some of the important parameter in terms of the protein structure. Also they requires less cost and less sample, right. So, one can have a real world example how like a case study I am giving you for COVID-19 spike protein vaccination development that has happened. You see, this is the case study that I want to discuss with you. So, there is a context of rapid vaccine development we are doing, right. We wanted to have as quickly as possible a vaccine that can be given to everyone and now we can roam freely around. We are locked in the house, right. So, if you remember those days. So, rapid vaccine development for SARS-CoV-2, this was our virus and we needed to validate that antigen structure that before pre-manufacturing. So, objective was to confirm the spike protein, a secondary structure and that has to match with the reference standard. You know, vaccine sometimes we mimic the virus protein structure. So, we measure this, we produce this recombinant S protein which was done by Moderna and Pfizer. They measured the far UV CD spectrum at 25 degree at different concentration, expected theta, the ellipticity was this much 62% helix. Now, we wanted to manufacture this scale attempt 1 and we got this much, right. So, it is a 65%. The assessment was it was passed. Take another lot, we are manufacturing same protein by another cell which was CHO cell or HEK cell. Theta was this much and because this failed because this was 52% helix. So, we wanted 65%, it has to be 65%. So, action is optimize your CHO cell expression and retest that whatever we are producing in say our lab is matching with the expected structure. So, outcome CD saved about $2 million in manufacturing and scale up by detecting the host cell dependent misfolding and CHO condition. So, it can be do again go back check the CHO cell or HEK cell and do the production. So, not only money was saved, but time was saved and we could save money and time and millions of life by doing this. So, with this there is a like in this lectures that we have taken from various sources, and if you are more interested please go and start looking at this original reference. So, here primary and tertiary structure textbook that we have taken, the practical guidelines we have taken how you do for protein structure determination, DNA and RNA structure determination, clinical application and disease application, also given you biosimilar and therapeutic protein characterization and how you can employ this in vaccine quality control, and one case study that I gave you about the spike protein conformation based vaccine that was developed by a few of the pharma companies Pfizer and Moderna, how CDs could save the millions of dollars for making a better vaccine, saving the life, saving the time, saving the money. So, with this let us stop it here. Thank you very much and I look forward to have you in the next class. Thank you.